Hello everyone, welcome to Conf42 Cloud Native. Today we are happy to talk about Chidori, AI and ML cluster management developed by Incorta. Let me introduce myself first. I am Ahmed Gaber, but you can call me Biga. I am a cloud engineering manager at Incorta. And also I have today with me Nadine Khaled, cloud engineer at Incorta. In our agenda today, we will talk about how Spark operates in Kubernetes, identify some challenges involved, and explain how Chidori can address these challenges, and also we prepared a good demo for you. Let's dive into how Spark works on Kubernetes. As you see in this diagram, the client will start to submit the Spark job into Kubernetes. To run the Spark driver in Kubernetes, we have two modes. First one is the client mode, which means the driver will still running in the client side. The second mode is cluster mode, which means the driver will be running as a pod inside Kubernetes. Once the driver started, it requests from Kubernetes to start the executor pods. So the Kubernetes scheduler will start to allocate the executor pods inside Kubernetes. After this executor pods created, the driver will be get notified to start to schedule jobs in these executors. So as you see here, Spark will get benefit from the Kubernetes scalability features like the cluster horizontal scaling for the node itself. So if you have pods to be allocated inside the nodes and there is enough capacity, cluster will be started to scale up to add new nodes to be more flexible with your job. And also you have like a resource management to ensure that the driver and executor running within your capacity. We figure out some of good insights on that model. First one, as I said, the cluster auto-scaling. Cluster auto-scaling give you the flexibility to get the better performance with low cost. So you don't have to have like a node to be up and running almost the time. Also, we found that enable the dynamic allocation give you like a flexibility inside the application itself to scale in and out the executor itself. Also, use spot nodes with Spark workload will save the cost a lot. This will give you a flexibility to get higher performance with low cost. Also, we notice most of Spark bottlenecks come from the shuffling issues. So to optimize your Spark job, you have to attach the Spark job into fast local SSD based on your cloud vendor to optimize the Spark scratch space. In summary, running Spark on Kubernetes not only optimize resource utilization and reduce cost, but also enhance the overall performance for your Spark application. While running Spark on Kubernetes brings us a lot of benefits like better resource use and the cost saving, it is not without its challenges. Let's dive into some of these challenges you might face. Firstly, the naked pod, which mean like when spin Spark job as a cluster mode inside Kubernetes, as I said before, the driver will start running as a separate pod inside Kubernetes. This pod is not controlled by any of replica controller or stateful set or deployment object in Kubernetes, and this creates some kind of availability issue for this pod, and it will be like act as a single point of failure. So which mean if this driver down for any something, your job will completely fail, and Kubernetes will not have any controller to spin this driver again. The second challenge is around driver pods distribution across nodes and its implications for cost. Driver pods are allocated across nodes based on resource request and node affinities. However, as job conclude, you may observe scattering of some pods across the nodes. Due to the constraint imposed by the naked pod issue, this distribution can prevent scaling down of a node to optimize running cost. Another challenge is around startup time overhead. This is time will be come from two factors. First one is if a new node is required from a driver to be allocated or executor, so the job will there is a latency to wait this node to become available. Also, another factor is the startup time of the pod itself for the driver. If you're using heavily Python libraries to start your job, so you will wait to install these libraries and configure some configuration for this job before the pod become available. So this will impact also the time to job to be executing once it's submitted. Another challenge is the Kubernetes scheduler itself. To understand this issue, we must understand how Kubernetes allocate pod to the node. This scheduler is called kube scheduler, is watch that from the API server in Kubernetes. Once the master get a request to create a pod, so the scheduler will start looking to available node to be hosted this node based on the resources constraint defined by the pod definition itself, and also node affinities. Once the scheduler find feasible nodes to host this pod, it will have like a scoring to find the best match for this node. Also, if the scheduler didn't found any feasible node to host this pod, the pod will remain unscheduled until the scheduler find best match node for it. So what is missing? Kubernetes will built for running microservice with scale-out architecture in mind. The default Kubernetes scheduler is not ideal for AI and ML workload, lacking critical high-performance scheduling component like batch scheduling, permission, and multiple queues for efficiency. In addition, Kubernetes is missing gang scheduling for scaling up parallel processing AI workload to multiple distributed nodes. Also, most of AI and ML jobs require an array of libraries and framework, including wheels, eggs, jars, and framework. This diversity requires a robust tracking system to ensure everything within our container image is up to date and function as expected. Moreover, the size of container images become critical consideration. As we add more components, the images grow larger, which can slow down the deployment time and impact the efficiency, and also adding to that, managing compatibility and upgrade of these versions. So another challenge to run any Spark or ML job inside Kubernetes is it's related to a concept called topology awareness. Mainly, scheduler will allocate the pod based on the resource request and pod affinity, which is defined by the pod itself. However, the node state itself is managed by kubelet. It's another agent running inside each node in your cluster to know the state of the node itself. So, for example, if this node have a disk pressure or some kind of throttling in some resource, so you need to be have like awareness before you allocate this job into node. Also, you must utilize the node affinities and pod affinities together to get the best match of allocating pods to nodes with Kubernetes scheduler. Another challenge is related to integration and monitoring. In Spark and Kubernetes, to monitor your job, you have to use Spark UI Master or using Spark History Server. These tools mainly concerned about the job. It's job focused and it's concerned only about the tasks or the stages and some kind of resource monitoring of infrastructure. But it's missing the correlation between the cluster behavior, the Kubernetes behavior with this job. So you will find some difficulty to troubleshooting some issues you may face. Also, the integration with third-party tools. to the current way to submit any job, as we see in the first slide, to use the Spark submit command, which is a CLI command in Spark. So it's not friendly to be integrated with other tools. So after addresses all of these challenges, we starting to build our beloved solution is Chidori. So we started build Chidori with a mindset to solve all issues that I listed in the previous slides. By solving the naked boot availability issue, provide more stable framework to run the Spark or ML jobs inside Kubernetes, and also provide well-integrated REST API with third parties, and provide more clear monitoring to correlate different factors to have a good troubleshooting for your jobs inside Kubernetes. So in this diagram, I will explain the high-level design of Chidori. So let us start with Chidori server. So as I said in first slide of the issues, that we have naked boot availability issues when we run our driver inside Kubernetes. So we built Chidori with a concept to be like a hosting for Spark drivers inside Kubernetes. So Chidori will host the Spark driver, and Chidori itself is a Kubernetes deployment. So it's totally managed by Kubernetes to guarantee the high availability and scalability also. So we build API server that provide multiple APIs to be deal with Spark in Kubernetes, like create job, delete job, listing jobs, and get logs. So this is API will be it's integrated with the Spark submit client, and also integrated with any third parties that can be integrated with Spark on Kubernetes server. So once we receive a job inside Chidori, it will be queue. And we build the queuing because we want Chidori to be control how much driver can be run at a time. So the admin can configure the maximum number of jobs and the maximum allowed memory and the CPU to be consumed at a time. So once the job received in the API server, it will be stored in our queuing system. We provide interface for multiple queuing system like RabbitMQ, Cloud PubSub, and Azure. So once the job queued, if there enough capacity to job to be run, the scheduler will fetch this job from the queue and start a go routine function to run this job. And the core engine will start tracking this job to manage all the life cycle of job. And all of this metadata stored in our backend store for monitoring purpose and auditing. Also, we build Chidori to be like interface with many of Spark vendor provider like Incorta, Kubernetes, and Databricks. So you can use Chidori to submit jobs to Incorta, or your own cluster in Kubernetes, or your cluster in Databricks. Also, we build like a monitoring to monitor the jobs, running jobs, and get full monitoring capabilities to correlate different factors while you troubleshooting your jobs. Also, we have a connect layer that provides Spark Connect interface with other parties. In the client side, also we will provide our Spark Submit Chidori version that easily integrated with our Chidori server. So you can consider Chidori is a full AI and ML cluster manager in Kubernetes that provide a full integration with Kubernetes and also different tools in ML ecosystem like ML flow and key flow. So you can focus on your business logic by developing your model training and deployment and serving, and Chidori will take care about infrastructure management. So now is the demo part.
Hi everyone, as mentioned by Bega, this is Nadine Khaled from Incorta Cloud team, and today I'm going to demonstrate with you how to install Chidori on your environment and put it into action. So as you can see here, we provide hand charts for AD installation into your namespace. So once Chidori is installed, you can verify if all the infrastructure components are created. And by infrastructure components here, I mean Spark server deployment, which is in our case is Chidori. And we also have RabbitMQ stateful set, which is responsible for queuing the jobs, and Chidori core deployment, which is responsible for monitoring the jobs that you had run before. And also, as you can see here, we have created all the necessary services that are responsible for making the deployments communicate with each other. Also, Chidori simplifies the management of Python packages. So you can install the Python package that you want to install for your job execution, and removing the hassle of installing it manually. As you can see here, I have installed Python package TensorFlow, and all these packages are already pre-installed in Chidori, so you don't need to install them again. Also, through Chidori, you can submit your Spark jobs through any Spark master, whether it's Kubernetes or Databricks or Databricks or Azure HD Insight. Also, Chidori offers the flexibility in specifying the driver memory that you want. You can choose the size for the driver that you want. So let's go back to Chidori setup. Once you made sure that all the pods are up and running, you can start submitting your Spark jobs through Spark Submit, and you can open Chidori monitoring for to see the status of these jobs. As you can see here, these all the jobs I have created before. I can filter by status, whether it's failed, whether it's succeeded. I can also filter by the date the job was created, and I can filter by the schema name and the table name of the job that was created. Also, you can preview the history of the job that you have created with the same schema name and table name. As you can see here, these are the jobs that was created with the same schema name and table name, and these are the status and all the information about them. You can also view this history in a chart view. So you are going to see how long these jobs took in order to be loaded or created through Chidori. And also you can do some actions on the jobs. You can download Spark driver logs, and also you can open this job in Spark History Server, as this will redirect you to the Spark History Server. Also, Chidori provides a shareable link feature. So when you want to share with someone the history of the job or any details or any information about the job, you can just give him this signed URL. So you will remove from them the hassle of logging to Chidori monitoring with credentials. So as you can see here, you just copy the URL, the shareable link, and the person that you gave him this URL, he will open this link and he will be able to view the history of these jobs. And he can display it, as I said before, in the chart view, and he can display details about each job was created. So that was Chidori, and I hope you enjoyed the demo.
So thank you to attending our session, and have a good day.